I'm going to present, introduce a new approach. Excuse me, can you 1 second? Have you turn off the sound, please? I'll come back right away. Thank you. Yeah. I'm sorry, the heater was kind of noisy and distracted. I turned it off. Okay, so today I'm going to present a new approach or a new perspective to lead time acceleration. In particular, I'm going to introduce an intrinsic relation between the speed of light in the cosmic void and the rate of expansion, rate of cosmic expansion in the during the late time epoch. So this relation is kinematical. It is also empirical. I'm going to deduce that relation from the observational data of the, in particular, the Pantheon catalog for supernovae. All right. In order to do that, we need to flip upside down our usual interpretation of the observational data for late time acceleration. So, now I'm going to move this screen. I cannot really move the screen. Huh? How can I move the screen to the next screen? Oh, it doesn't allow me to do that. Huh.
In the keyboard, you can go through it?
No, it doesn't go through. It does here. Okay, here I see my. How can I move? I cannot really move. I cannot really move. Maybe I upload. Now can you see my screen still?
Excuse me, sir. Actually, you should share your entire. Now it is going. Yes.
Oh, can you see my next screen, right? Yeah, this slide. Oh, okay. Thank you. Okay, yeah. So this talk is based on a recent article I posted and a few other articles that I published last year. And so here the list. So first of all, let us ask ourselves why we have to revisit the late time acceleration. We know by now that lambda CDM cosmology can explain a lot of observations in cosmology in general, from late time, early time, and many things. But also we know that it requires an important component, that is the dark energy. Of course, the energy will come with a heavy price. First of all, what is dark energy? Nobody knows what it is yet. We also have the fine-tuning problem. We also have a why now problem. Why the lambda, the value of lambda for the density for lambda or the density for matter is approximately equal to each other today. We also have hypotension, which is about the 5 sigma discrepancy is about 7% difference. And also we have a lot of new properties that keep popping up every day. You know, we have a phantom dark energy, we have early dark energy, we have dynamical energy, and so on. And so the more and more problems that we are facing with the lambda CDM should suggest something, perhaps that lambda is not a real physical entity, but it shows a limitation in our understanding of gravity. And so we need to revisit that. So here the strategy I'm proposing, and that is the kinematics and dynamics. So let us revisit what is that. Now we have the Robertson-Walker metric. This is the form for that. We know that for unstandard universe, the form for AT is proportional GT equal to 2/2. And with that universe, with that form for AT, we cannot fit with the high Z section in the Hubble diagram of supernovae. And that was the key motivation that lambda term was added into the Einstein-Hilbert action. And from that, from with the lambda term in and the answer for action, we solve for the Friedman equation. Friedman equation will give us a new AT. So the way the lambda CDM handle the Fibonacci Hubble diagram is that you change the AT here. Right? So instead AT equal to t equal to half q third. Now by adding in the omega lambda, which is about 70%, then now the AT will be modified to this form, right? And you can see that this form contains one preferred time scale, t lambda, which is this one with about 11 billion years, which is quite recent. And so therefore that is the problem we call the why now problem. So in the current paradigm of cosmology, such as the lambda CDM or many others modified gravity approaches, such as, so we start from, the way to do is that we start from some dynamics first. That means you propose an action. Be it, let's say we take the lambda CDM, you can add in torsion, you can add in non-metricity, you can add many things like different kind of action like FR, FT, and FQ, many things, right? And from that we solve for from Friedman equation, we derive the AT, the function AT here. And of course after that we fit with the data, right? So we do that. And the point is that we start from a dynamics first and we derive the kinematics from that. And we are pretty confident in doing that because nowadays we know that, okay, we start from dynamics, we know general covariance, we need the action to be general covariance. We add in some other symmetry that we think of, right, like torsion or other things. Okay. Now, however, I'm proposing a new strategy. What if flip the order around? First of all, we infer the kinematics from the data. We let the data speak. Then after that, we will seek the dynamics. We find dynamics that reproduce the kinematics. So therefore, the order will be different. That is, we propose we find the kinematics first and dynamics later. Right? And in history, there was one beautiful example. And that is the case for in the 1600s, 1619 by Kepler, Johann Kepler. So he started from the Tycho Brahe catalog of planet in motion. Then he derived the three laws of motion for planets. That is kinematics. And about 50 years later, then Newton started from the Kepler's law to derive his universal law of gravitation. So that means that in this example, they start from observations. And they come up with kinematics, and after they come up with dynamics. And this is one of the examples that the little known fact, that is, if the same elliptical orbits in this case, so in this case you have the two cases. The one of them is that both of them have the planets move on an ellipse. However, the location for the sun is different. If the sun is at the focus of the elliptical orbit, this one will be the first Kepler's law, right? So Newton was able to show that the law of attraction would be the inverse square law. So F would be inverse of 1 by r squared. That's Newton's gravity that we know. But if the sun stays at the center of the ellipse, then another story. That the law now is Hooke's law. Now the force is proportional to r instead of 1 by r squared. Right? So the key thing is that just by moving, you have the same elliptical orbits, but just by shifting the location for the sun, then you have an entirely different dynamics for gravity. It's very sensitive to that. So therefore, this illustrates the key point that the kinetic is crucial, tells us a lot about dynamics. Right? And interestingly, Newton knew this, and he posted it result in his book Principia. And I invite you to see the Feynman Lost lectures. In that, he discussed this problem, and also if you can go to the YouTube channel, I post a link right here. So let's do that. Oh, can I open this one? Connect, I suppose so. So this is very interesting. Yes, this is very interesting. The YouTube here. So if you go here, so here. Okay, so I invite you to watch this one. Okay, so therefore that I'm going to skip that. And excuse me, how can I go back? Okay, here, cool. Then let me go back to that. Okay, good. So I invite you to watch that YouTube video, which is very educated. All right. So therefore that we are making the same analogy here. So instead of from Tycho Brahe catalog, from observation to kinematics to dynamics, we have the same thing. We will start from Pantheon catalog observation. We're going to deduce some kinematics for cosmology first, and after we find the dynamics that suit that kinematics. Okay? So therefore, that we start from the general Robertson-Walker metric again. But in principle, this C here doesn't have to be a fixed number, a fixed constant. We can allow, in principle, that in Einstein theory, he imposed two assumptions. Number one is that C is fixed, and number two is that the action is unforeseeable. Okay, so those are the two, not just one, and two assumptions. Anyway, so we can relax that requirement on C to be a fixed number. Let C to be dependent on the cosmic scale factor as well. They're very generic. And again, our goal is to find out how the supernovae Hubble diagram actually tell us about the kinematics AT and CA without a priori assuming any dynamics beforehand at all whatsoever. Okay, and of course we need to parameterize these two functions because the function we have to parameterize them. So I'm going to adopt some parsimony. So I will adopt the form for AT. I will adopt the form power law form used by Don Gott in about 30 years ago. For the CBAT, I'm adopting the John Barrow's answer here. So via power law again. The power law functions are advantageous because they are free of any preferred scale, right? Because T0 is not a scale. T0 here is just a number, just a coefficient outside. It's different than the previous one. For this case, this T lambda cannot be put up. This T lambda is real preferred scale. Okay? And so in this case, the power law are free of any preferred scale. And that means that this kinematics would be free of the why now problem in lambda CDF. Okay, I'm going to make a claim here, the bold claim. The claim is that the supernovae Hubble diagram support this intrinsic relation between speed of light and the expansion rate of the cosmos proportionally in these two. Okay, so therefore the speed of light and the dABDT, the expansion rate here are in sync at all instant in the lifetime ever. And of course, you see from here is important because it's intrinsic. That means that if this relationship is correct, is true, then you cannot say that the intrinsic. That means you cannot just arbitrarily change the unit of length and time. Because the moment you change the length and time unit so that C varies, C different, then this also, the second term will also vary, such that they are directly proportional. So they are synchronous, and that synchrony is independent of the unit that you choose. Okay, that's important. Now, okay, so one thing I need to make a statement here categorically, that is the Lemaitre formula, 1 plus C to the A to minus 1 here, cannot be used for VSL cosmology. VSL stands for variable speed of light cosmology. And in the past 30 years or so, a lot of authors have used VSL to apply for Pantheon data and so on. And they reported time bound on variation of C during the cosmic time. Unfortunately, all this work rely on the Lemaitre formula. And I will show in this case, I argue with you that this relation does not hold for VSL cosmology in general. And that means that these bounds are not valid or questionable. So the reason is this. Imagine that we have a universe. This one is different galaxies. I'm just plotting the two-dimensional projection here to be easy to see. Now, the host galaxy with a supernova here, and with a light wave, and it transferred to us. We are sitting deep inside the galaxy, the Milky Way. So during this time, moving from transit from the host galaxy to the Milky Way, the light wave will stretch out due to the cosmic expansion, as we know. So in VSL cosmology, the speed of light outside here would vary. This point is different from this point, right? However, everybody in the field of VSL implicitly assume one thing I did not know about this, that is the speed of light inside the galaxy and outside it are the same. That is their assumption. However, this is questionable because the universe expands, and so therefore that the speed of light outside here can vary. However, we are sitting inside the Milky Way, and the Milky Way is gravitationally bound object. It does not expand. And so therefore that we can safely assume that if the speed of light inside the galaxy stays stable over time, despite the variation, the changing of the speed of light in the cosmic void. Okay? The same thing here, that means that inside here, we're sitting here a billion years from now, the speed of light inside here is still the same number that we know, 300,000 kilometers per second. Although the speed of light outside the galaxy here is subject to the cosmic expansion and can vary. Okay? So therefore, we have different the speed of light inside the host galaxy and the speed of light outside here, and this very from here, and inside different again. And so therefore, we cannot assume that these two speed of light inside and outside here the same. Okay? And so here the picture you can see from here that inside the host galaxy, the speed of light CSN, supernova, to put that. You have a C1 outside here, and then expand to C2, and inside the Milky Way you have CNW. Okay? So therefore, in general, we don't have that. In general, we have CSN, C supernovae, different than C1. And the C Milky Way here, different than C2. Right? Now, the light wave has to make 3 transits in its way to the observer inside the galaxy. This is the transit 1 from inside the galaxy, host galaxy, to the cosmic void. And the second one, the usual one, would expand from here to here with the cosmos. And the third one, when he entered into the galaxy, Milky Way. So 1, 2, and 3. And so for the transit 1 and 3, right here we have a refraction effect due to the transmission of light wave across a medium with different, with the varying velocity of wave. And so therefore, there is the wavelength with on the right here, right? So therefore, that we have lambda Sn inside, it changed to lambda 1 because of the refraction right here. Lambda 1 to lambda 2 is the usual cosmic expansion. And lambda 2 to lambda Milky Way is the change in this, the speed of light, right? Now, and we have to notice that the supernova emit lambda Sn, not lambda 1. And the same thing here, that we observer will detect the lambda Milky Way, not lambda 2. Right? That's important. And whereas the lambda 2 and lambda 1, the ratio between them is usual as A inverse A, that's known. However, what we detect in lambda, we have to compare lambda Milky Way with lambda Sn. And that is not lambda 2 but lambda 1. And so that's why the Lermite formula doesn't hold anymore. Okay? And you see from here that this one, the formula general here. Now, if lambda Milky Way and lambda Sn are equal to each other, because we say that the galaxy do not expand, and so therefore, if they stable, and so therefore that you have this extra term C1 per C2. Okay, so therefore that already affect the Lermite formula in a fundamental way. Only if when lambda Milky Way and lambda 2 equal to each other, and lambda Sn, C Milky Way and C2 equal to each other, and CSN and C1 equal to each other, then these two terms cancel out exactly, and we recover the Lermite formula. but that's a very strong assumption. And in general, it doesn't hold that way. All right. And so therefore, and I tell you that I recently reviewed an article about VSL, and they pointed out to the author that is the Lermite formula cannot be correct anymore. And fortunately, that the authors and the editors agree with me on this, and they wholeheartedly agree with me on this. They embrace on this argument, reasoning. All right. So excuse me, what time is it now? Okay, I need to be quick there. All right. So let's summarize. Then the classical Lermite formula doesn't hold anymore for VSL in general. And I will leave the definition aside. And now you see from here that from here, let's suppose if you ignore see this term, suppose that see the Milky Way and see supernova here the same. And in that case, you have a ratio of C1 by C2 right here. And that introduces an A, because we assume A to be here, A is C to be A, this form, right? Zeta. So therefore, that it adds into another term right here. So therefore, we have this term. Forget about this F for the moment. We have this term, right? So we have a zeta right there. Now, the Fz I put here as a function for account for the ratio between the speed of light inside the Milky Way and this host galaxy, because we don't have a reason to believe that these two are the same, right? Because the host was existed a long time ago, billion years ago, and we are now today. So they may change a little bit. And for that, I put in the function Fz, that ratio, to account for the difference of C inside the host galaxy and C inside the Milky Way. Okay. Now, so that's the formula. And of course, if you assume you take the case of the limit of C Milky Way equal, so we have this stuff. This form. It's different than the Lermite formula. And from here, that it interestingly from this new Lermite formula, modified Lermite formula, and we have the modified Hubble law. Okay, and this Hubble law that the Z and D for the low Z and for the low Z limit, then Z proportional to D as usual. However, the coefficient is different. The coefficient is no longer H naught as usual, but it is 1 plus zeta of that. And this is important because when we measure the Hubble value, Hubble constant, we plot Z as a function of D. And in that case, the slope for this plot would not be H naught anymore, but 1 plus zeta H naught. Okay, and this coefficient, we know value will be around 70 numerically, right? And we often identify that 70 kilometer per second per megaparsec to be H naught. But in VSL, that's not the case anymore. That is, we have to divide that 70, the value 70 by this coefficient. Okay, and if zeta is positive, that means that we have a reduced formula in H naught. Okay, I will come back to that point, very important one later. All right, so the derivation of the distance redshift formula can be done, and I showed it in my paper, and it can be done like in closed form. And so that's the closed form, and it depends on mu zeta and the H naught. See this one 300 kilometers per second as usual. The F here is the function, I say, is this one. We have to do it phenomenologically. And so I parameterize it in the one form, in the one parameter form. So Fz would vary monotonically from infinity, from today up to backward to the Big Bang, so Z infinity, and with one parameter F infinity. So for a given pair of mu and zeta, this formula has two parameters, H naught and F infinity. So let's compare with the uncertainty zeta. This one we know from uncertainty zeta and the lambda CDM. The lambda CDM also have two parameters, H naught and omega lambda. Okay. All right, so do the fitting. Let us reanalyze the pantheon using the DSL formula. Now, this is the result. And we know that this one is they actually the same, this one, the same picture. This one only the log scale for redshift. So the combined pantheon sample composed by Skolnick and Dan Skolnick and collaborators in 2018 has 1,048 data points without the bars. Now the long dashed line, sorry, no, we don't see it because it's indivisible. So this line is okay. So the EDS, if we use EDS to be x naught to 70, it will be that line, right? The low line here. We know the high Z is the data doesn't fit and don't fit anymore. It's some excess modulus right here. And the lambda CDM, we have x naught to be 70 and omega lambda to be about 70%. So it fit very well with the data. And that has been interpreted as the direct evidence for dark energy. However, if we use our formula, we have a solid line. I'm showing you the case for the mu equal to 2/3 and zeta equal to 1/2. And this is a very important case. I will come back to this revisited momentarily. And now you know the two lines for the lambda CDM and the DSL formula here are indistinguishable. We don't see the difference in this picture or whatsoever. Now, this one is resolved if I allow mu and zeta to run independently. So again, for a given pair of mu and zeta, I optimize, let me go back to this formula. For a given pair of mu and zeta, I'm going to optimize the x naught and at infinity so that the modulus would fit well with pantheon data. Okay? So this is the result. And so I vary this value for the whole grid here for different mu and zeta. There are 4 cases, so therefore this one is the 6 in the black band is the 68% confidence level. And the gray bands are for the 95% confidence level. And for this power law cosmology, you know, the yellow dotted line is this form 1 plus zeta mu equal to 1. So that is decay like this along that line. I'm blocking the 4 cases. So again, let's look at the table. Lambda CDM for the benchmark for omega lambda about 70%, 61%. And the x naught is 70. We get chi-square to be this level. Right. Now the 4 cases, the EDS case, answer the zeta, the mu equal to 2/3, zeta is 0 because there's no speed of light change there, and f equal to 1. In that case, the chi-square is 2.3, it is very bad, and that was the reason why cosmologists had to introduce lambda. The Don Goff case, Alexander Don Goff, he introduced this one about he did this one about more than 10 years ago. And there was another group with Planck, Tutu, and so on also study that. So they put the case to Don Goff. They consider this case with the power law cosmology only, but without C vary. And again, we take the chi-square here. I plot it for completeness. But there are 2 more cases. The cone case is the Costin universe. In this case, that the universe span linearly with time. Okay, so this is equal to 1 and speed of light 0. There's a change. And if I vary also f infinity to some number, and we get this value, chi-square. And the case I mentioned that VSL EDS. VSL EDS, we have the same EDS here. That means that the A is grow at the T equal to 2/3 as usual at the EDS, meaning without dark energy. But let's allow zeta to be 1/2. That means that C declines over time as universe time. Now, the chi-square is, you can see from here, the cone case and the VE, the new case here, the blue case here, outperform lambda CDM. And that's exactly why that it fits extremely well with that. Again, with the 2 parameters, x naught and f infinity. But one thing striking, the x naught now only 47 in a 70. This one. Okay? And the reason is that I'm going to say to you, that is, let's go back to this, because even though the coefficient right here, the slope of z versus v is 70 kilometer per second per megaparsec, but because zeta is 1/2, so the whole thing is 3/2. So 3/2 of x naught gives you 70. That means x naught about 47. Okay. Now we still have, even though x naught is low by the cut down by factor to 50%, but T0 is still about 40 billion years. Okay, so the 3 numbers are still okay. All right. All right, so instead of plotting this way, I'm going to replot instead of mu versus zeta, I'm plotting mu versus mu zeta for reason. So this is the case. So this picture is exactly the same this picture, nothing else. But the nice thing is that the locus 1 plus zeta mu here equal to 1 become a straight line in this plot, and the 68 and 95% confidence level become like that, right? So it hugs with this line pretty well. And again, this one is just I use the data to produce it. I'm not trying to fit anything the data with this curve at all whatsoever. Okay, this one I let the data tell us what we have. Okay, so that's the case. And now I can plot also if I can do the marginal line, we integrate along this line, and this one the distribution of this property, this quantity, 1 plus zeta mu. So along this line, 1 plus zeta mu multiple mu equal to 1. Away from it, this is bigger, this is smaller. Okay, so integrate that along in this curve, and that's what I got. So we have a full distribution of this stuff, 1 plus zeta mu. It gives us a peak at 1 and almost symmetric around this with the width about 0.2. Okay, that data tells us. Okay, I did not impose any dynamics whatsoever in this case. So we have a remarkable degeneracy along the line, the locus, 1 plus zeta mu equal to 1. This is an empirical fact because there's no theoretical reason why the Pantheon data should obey that line at all whatsoever. Yet the data tell us it is. Okay, it tells us that it should obey that. So this one is it confirms that posterior. Okay, so therefore that let us take this one for as a empirical fact. So what can we do this? So we have a conformity related to that. Nice. Now, if we assume 1 plus zeta equal to mu equal to 1, then we see from here because C proportionality, right? Because again, let us C equal to A equal zeta, right? But A is T to this stuff. And so therefore that we plug A into here. So that what we got here, it will be A raised to C become proportional to the minus zeta mu. But zeta mu equal to mu minus 1, right? Because from this relationship, so we have that. Now, A is proportional to T equal mu. We take the derivative of A to time. That we also get. And so therefore that C and A dot are proportional to each other because both of them share exactly the same distance. So that's what we got. Okay, so C and A dot are proportional to each other. At the moment for this term is still mu, but we also know that T naught by mu equal to inverse of H naught. So therefore now we've obtained a relationship. C is this. Okay, equal to C naught by H naught A dot. This relationship is nice because it only contains the physical measurable quantities, C naught and H naught. It does not depend on mu. This is still depend on mu, but I don't transform it. So therefore, this is kind of model independent. Okay? And this happened on time, at least for the late time ever. So that means that in the late time epoch, if this relationship holds, then the cosmic expansion rate is in exact synchrony with the spirit light on instance. And this feature is absent in lambda CDM model. And I need to emphasize again, this relationship is intrinsic. That means that if C and A dot are in synchrony, then it does not depend on the unit of time and length. Because the moment you change the length and time so that you change C in some way, then also change A dot as well. Right? Because C is a kind of a speed of something, of a light. A dot is also the speed of something, the speed of galaxy receding from each other. Okay, so therefore these two speeds are parallel, proportional, and so therefore that relationship is intrinsic. It does not depend on how you change the units. Okay, but the lambda CDM entirely miss that relationship. Okay, because in lambda CDM, C is fixed, meanwhile A vary with time. Okay, and so that this simplified, you mean the X naught here, right, vary with time. sorry, the Hubble constant. Very good time. And if we assume, if we adopt this formula, then we have the Hubble sphere is proportional, dx will be grow with equal to a, and that means that we preceding speed between two galaxies is always synchronous with the speed of light at that moment. And I'm going to skip this one because that means that we are not in any, in the principle we know that the Copernican principle that we are not in any privileged space in a large scale location in the universe. But not only that, this relationship means that we are not in any spatial time whatsoever in the universe. Okay? So that will generalize the cosmological principle into the time domain. All right. So interestingly, that if we have that C and A dot to be proportional to each other, then the Robertson-Walker matrix here can be transformed further. So we put C equal to A dot. That means that we put here C. So this first term become dA because C is dA by dt. So therefore this become dA square. Okay. And of course we have to rescale there's some coefficient right here, but we upper rescale it. We can redefine R and T so that this one becomes that. Very nice. And if we set A equal to exponential of eta with some conformal time coordinate unbounded, and that becomes this. And so we said that this matrix is conformally equivalent to the Minkowski matrix. This part is Minkowski, the whole thing is Minkowski with the conformal factor. Okay? So this is not the linear universe. The linear universe has negative spatial curvature. The universe I'm considering here is zero spatial curvature. Okay, but also that because of this conformal, the Minkowski proper part here. So this universe, the past light cone and the future light cones have no, extend to infinity, and so therefore we have no. This universe does not have any horizon, both from the cosmological for the past light cone and the event horizon for the future light cone. Okay, that's nice. Now, what can you do first? Now, if we go back to this case, let's assume that we are along this line. Suppose we take this line here for granted. Let's say that this line is real. There's some real reason, maybe some fundamental reason why that happened. Okay, along that line. And if we go back to the formula, in that case, that when this one is equal to 1, and you have to take the limit because it becomes 0, it becomes 0 as well, and so we take the limit, and that limit becomes this. Then becomes this. So along that line, that formula reduces this. Okay, we have a logarithmic here. And in the limit of high redshift, this 1 plus z becomes z, right? Because z dominant 1, z. This will become a constant, f infinity. We ignore that, and log become log z. So the high redshift, our formula becomes z log z. Okay? But if we look at the EDS formula, EDS, z is high. When z is high, so we have this becomes z, and this becomes 0, only z. So the difference between the DSL formula with the EDS is in the log z term. Okay, but we have same z. That means that now we have the extra log z. That extra log z gives enhancement in the modulus for the DL at high z. Beautifully, you get that. So that means that the distance supernovae will appear fainter than expected from EDS. So the EDS model cannot explain that. The high z section for the supernovae Hubble diagram. But the reason why this helps because you have a log z. It captures very well. And you see from here, sorry, I go back to that. Right. So this one be that, but now this one is this is modulus versus log z. So you can see that then you have an extra term on top of that. So therefore that part lifts upward. Okay, so that explains why. Now, all right. So therefore, the synchronous behavior between C and dA by dt is responsible for the SS modulus in Hubble diagram high z. And so therefore that the Hubble diagram can be explained by DSL. And there appears to be no need for that energy at all whatsoever. at least for the Pantheon data. Right? I can give you another explanation. This one gives us the mathematics, but I can give you an intuitive picture. Why? Okay. So let's go back to the case of the EDS VSF, the EDS case. Let's consider the standard cosmology, and we are here today with the time slide T0. We look backward at some time T1 in the past with the supernova 1. And we look further for another one with the time, this one is 2 times as long. So therefore the supernova 1 and 2 have the relationship. So let's say that the redshift for Z2 is 2 times the redshift for Z1. Okay. And in standard cosmology, that the supernova 2 is twice as far further than supernova 1. And so therefore they appear 4 times fainter. However, consider the case with the VSL. In the VSL EDS universe, the light will travel faster in the past than in recent time. And that means that even though supernova 1 is here, supernova 2 is not here anymore. It has to start realize somewhere further because the speed of light, it travels faster in the past. And so with the same amount of time, it covers a longer distance, okay, than this one. Okay, this one covers this D1, but this covers this segment longer than this one. And so this one is not here anymore, it moved here. And so therefore that D2 is 2 times, more than 2 times for D1. And so therefore the supernova 2 will appear much fainter than supernova 1 but factor greater than 4 compared with the usual standard cosmology. And if we plot D versus Z, we see that instead of a straight line, you will start here. Now with an extra modulus right here, that's why we have something different upward. That is what we saw in the Hubble diagram for supernova. All right, good. So that produced an excess moduli for the high Z in the Hubble diagram, also known as late time acceleration, with the past 28 years. Now we have a new interpretation. I know this is bone interpretation, reinterpretation, that the universe is not accelerated, but the speed of light is decelerated in the expanding EDS universe. So the underlying cosmology is still EDS. There's no need to introduce lambda. However, the speed of light is declining. Okay, that's an entirely new interpretation. And so I give you this one to explain mathematically, but also I give you the intuitive picture behind that. Okay. Now, let's move on to another consequence. And as discussed to you, the conformably flat matrix, this, due to the proper path in Minkowski, big Minkowski, so it has no horizon. But we can confirm that if we compute directly, if with this we can confirm that you can compute the horizon, cosmological horizon. We look from today back to the Big Bang, and in that case that we integrate and you have this infinity. And this property may resolve the horizon paradox without using cosmic inflation. And in this regard, that I invite you to read the paper by Moffat and Operation Maguayo in the 1990s. They discussed the possibility for that. Similarly, for the future horizon, event horizon, we look for the future light cone. Again, you compute that, infinity as well. Now, let me show you the idea, the proposal from Moffat and Operation Maguayo in 1990s. They proposed at the time that a high value for C in the past may explain away the horizon paradox without the need for inflation. And what we do is that now, suppose that we are here. We look at the time for the time for recombination event. So let's consider the two events A and B, two distant points across the sky, far away from each other. And the problem with this one is that A and B, we look back, the past light cone are causally disconnected. Okay, and so therefore A and B are disconnected. So why do we look the same across the sky? To the very high precision, 10 to the -5 precision. right? But these gentlemen proposed that, okay, A and B, now because of the speed of light, at least in the VSL proposal here, speed of light was faster in the past. So therefore the light cone, the past light cone expand outward. And so therefore that from the 2 point A and B, the light cone for A would expand like this instead of just the C constant, right? And B as well. And now instead of for that in the Big Bang here, the A and B are now were causally connected. And that is why A and B look the same in the sky. Okay, so that is the whole the idea from Moffat and Maguire and Albrecht. But I cast that in terms of the thing I show you here. Okay, so like that. All right. Let me see how much time I have. So, okay. So real quick. Now along the locus 1 plus theta mu equal to 1, we can also plot the compute the distribution for the joint distribution between mu and T naught, and that gives us that. The distribution T naught is kind of insensitive with respect to mu, which is around 13 and between 13 and a half and 40 billion years for the age of the universe, which is good. The EDS, VSLDS is right here. I plot that, is right that point, and the cone case right here. So the question is, how can we restrict the value of mu further? Because this value of mu kind of wide, right? I mean, we from somewhere, it's from 0.2 up to 1, it's kind of pretty long. So how can we restrict this range further? And for that, we have to need more data, especially data from, let's say, the CMB. So the CMB, hopefully, I'm speculating here, that if we apply the VSL cosmology to the CMB, hopefully we get something like, have another, let's say, the locus around here. I'm just speculating, okay? So suppose we have some line here. So the geogram cross and give us some restriction, constraint in the space for me. But that will leave for the future work of collaborations. Okay. Now let me go to the case. I have been mentioning the case of VSLEDS a lot, right? So here we have the 1 plus theta multiple mu equal to 1, but we don't have this one constraint between mu and theta. But it does not tell us anything about mu yet. Okay? Now let's focus on the case of mu equal to 2/3. That is the case for the unsundecided universe. We love that benchmark case. In that case, that zeta equal to 1/2, right? So 1/2 here is 2/3. So that will be that. So let's consider that case. And unfortunately, this one is contain a lot of material which I don't think I can cover today. And if you're interested, I can cover it in future seminar. All right. So very quickly, I gloss over this. So in the 2 article 1 and 2, which I put in the summary right here. I put the summary right here. To read that. Then I consider this is scale invariant reaction. That the dilatant field. Now this reaction is scale invariant, and the dilatant field now coupled directly with the matter field. So this is kind of a non-minimal coupling between matter with gravity, right? Because now the gravity coupled with matter coupled with gravity, not just through the Jacobian term right here, the determinant right here, but also to Chi as well. And within each concept, you can show that the dilatant field can play the role for both the Planck constant and the speed of light. So Planck constant and speed of light now depend on dilatant. And if the dilatant field varies in space and time, so do the speed of light and the Planck constant. And you can convince yourself, I mean, these are in the paper I showed that the Compton wavelength for the electrons, lambda, and the transition rate in the atomic scale would obey this relationship with the 3/2 right here. So lambda and dilatant field is inversely proportional to each other. But the time scale is related to dilatant with this coefficient 3/2. Okay, and so therefore lambda and tau now are related by this formula. Okay, 2/3. That is a 2/3. And if we apply for the cosmology, let's say we set the scale factor to be inversely proportional to that, to the dilatant. Then in that case, that C here now become depend on chi, and the chi depend on A, and so therefore that is the form we have. C is related to A that form. Okay, so that is zeta here is 1/2. And let's set it to A. This one is the time. So we have this one EDS. Okay, so this is the justification for the EDS VSL universe. Okay. Now, however, as I showed you before, so this is that case that mu and zeta, that the case, but we have x0 into 47 coming from the modified Hubble law. Okay, but we still have problem. Why is too low? How can we reconcile that? Is it, are we in trouble? Way too low. Are we in trouble? It turns out that after I finish my work in this value 47 here, I look on the internet. I mean, in the literature, you find out whether this value has been found elsewhere. And there was at least one. And two actually. This one by the work by these four gentlemen, Blanchard, DP, Robin, Robertson, and Saka. I will call them BDS for short. Another one is work by Tom Shine of University of Durham. Anyway, so they published in 26 years ago this paper, an alternative to the lambda CDM model. And they want to study the W map, the CMB W map. And what you do is they relax the hypothesis that the fluctuation spectrum is no longer the single power law, but they made it to be the break power law. Break power law means you have two sides of the, it's a power law, and so again, P is function of K. But now we take the high K and low K separately, and each of them, each part is power law separately. Very small modification. And what they do is, what they found is that the unspun certain universe with zero lambda whatsoever can fit the CMB very well. Very, very well. Even better than the lambda CDM model. The main concern for them is that now they get x0 to be 46 kilometers per second per capacity. And that is shocking. And they struggle with this because this number is too low. Okay? So by now they gave up the idea because at that time the x0, the value of x0 was still controversial. It's not clear the 70 or not. But they argue this can be a low bound. But of course by now they gave up because this is too low, right, compared to 70. So, but they gave up for wrong reason. Okay, so I discussed this in my paper here, but anyway, so this is their result. This is not my result. So we know this peak here. So again, you look at this W map result data. Okay? And if you fit with the dot line here, the dot right here, this one is the lambda CDM model. But now if we apply the Blanchard BP and Robinson Saka with the blue line here is lambda m, omega lambda is 1, I mean omega lambda m is 1, omega lambda is 0. And they have an excellent fit to the CMB W map. Excellent fit in there. The only change will be here, you see it from here. We use the broken power law with omega lambda 0. You have the excellent fit. Okay, we don't need that nature of server in that. So BDS only use EDS universe with no data energy to fit the W map data power spectrum. And they obtain x0 46. And now we have the agreement near identical between the BDS result for CMB and now result 47. This is truly striking. And I invite you to read my paper for explanation why they gave up and they should not have given up their result. Okay? But one thing is striking because I was not aware of their paper from the beginning. Only after I finished my work, I looked in the literature to find out whether this result, the 47, has been found elsewhere. And that shocked me a lot for this. So this one I kind of believe prediction. Okay? So therefore, the value of 46 and the value of x0 is lower than 70 is not an isolated incident for my work here, but also appear already in the CMB, which is an entirely different data set from the supernovae, right? Because CMB is a snapshot across the sky. Meanwhile, the supernovae is a longer time direction. So the two data sets are kind of perpendicular to each other or top of each other. but yet we agree in that value, and that is striking. All right. So what can we do with that value? So if we assume again go back to the EDS with x naught 70, and we apply the age formula now, we have only the age universe only 9 billion years, really too short for the older star. We're in trouble here. So by adding in the omega lambda, we have the different formula for the age, and that gives us about 14 billion years. It's okay, it's good. But look at it again. If we use the reduced formula in x naught about 2/3 smaller, this is exactly 2/3 of this term, right? So, all right. So in that case, we exactly the same apply that because the x naught now reduced by 2/3. So instead of 9 billion, now we improve it to 14 billion. And that fits perfectly with the 14 billion without using dark energy whatsoever. Okay. So in this case, we don't have any dark energy. In this, we do need dark energy, but with x naught to 70. Okay. So therefore, that we use the value of x naught, smaller x naught here, actually resolve the age problem without using dark energy. And okay, I have a few minutes left. I'll try to finish soon. So also, as I showed you the FZ, look back again for the formula for the luminosity, the redshift formula here, luminosity distance. And I showed you before, these are the formula. But the x naught here, but we also have this term FZ. So therefore, the whole thing here acts like an effective x naught bars. And it is actually like a running today value per Hubble constant. So depending on the data set, the redshift data set that we're using, the segment data set we're using, we have different values for x naught. Okay, it's effectively there. And this idea actually has been used by many people. They do bending, they do many things. But in this approach, now I'm proposing that exactly that why it should happen, because we have FZ directly from the change from the speed of light inside the Milky Way and inside the galaxy. And I plot that, and the FZ will be here, and I show you the FZ to be the 70%, I mean 0.93. Here. This is 7% lower than 1. Right? So therefore, look at it again, and we click here. So therefore, that this drop to 7% drop, and once it's very large, this term become x naught infinity. So therefore, this drop and rise slowly. When it's very very large, it approaches to again to the 0.3. And so therefore, from the supernovae data alone, the x naught at z extremely high would be 77% lower than x naught today. And this fit quite well with what we saw in comparison with CMB, C7, and 73. These 7% reduction as well. So these two match each other. So therefore, the Hubble tension can be resolved by using FZ. Of course, what I'm claiming is that both the x naught for the CMB and x naught for the local should be reduced by factor 3.5, right? 50%. Anyway, so I don't have enough time to discuss the cone cosmology, which is interesting, only because the cone cosmology with the K matter equal to quite strange. The K matter with the equation of state 2 to minus 1/3. Then the media and others already found some interesting phenomenology for BAO and the large structure formation. But I don't think I have enough time for that. I invite you to, read my paper on that. And this leads for future work, because maybe the BAO and the structure formation for media can be carried over into the case of PSL, EDS, as well. Okay, let's summary. Again, we start from general Robertson-Walker matrix flat, with C is a variable. For the Pantheon catalog, I aim to deduce how the universe stands without imposing the Y in advance. That means I do not assume any dynamical model. And in history, that we have analogy that Kepler derived kinematics, explain how planet moves. And Newton will later derive the dynamics, explain why planets move in such fashion. I parameterize AT in the power law and CA to power law. These functions are free of scale, so avoid the why now problem. The important point is that Lemaire's rest formula is no longer valid for VSL commodity, and we derive a modified version for it. This model gives excellent fit for your catalog, and moreover, it exhibits a strong degeneracy posterior, 1 plus zeta mu equal to 1. And if we assume that formula hold, then we arrive at an intrinsic relationship between C and the rate of expansion. And this is the single most important result of my talk today. And again, this relationship is between the two kinds of speed, and so therefore is unaffected by the change in length unit of time, the clock and rock. And this is empirical, especially in terms of C naught and X naught. So therefore, hopefully, it is a robust derivation. And if we further correlate that, this law will impose a strong requirement on the dynamics of cosmology. And currently, the lambda CDM does not satisfy the law. And indeed, because lambda CFC is fixed, but dA by dt varies. So therefore, it cannot satisfy this relationship at all whatsoever. And so if this law is true, then this is the most decisive challenge against the lambda CDM paradigm. And the synchrony between C and A dot, the dABDT, give us quite a number of things interesting. Number one, it gives us the SS modulus for the high Z diagram, also known as the late time acceleration without requirement D. Number two is that the horizon infinite without requirement inflation. And also give us a new conformal flat metric cosmology. So this one is the list of bibliography. And thank you for your attention. And we're open for suggestion for idea for future study and collaboration. Thank you.
So thank you, Professor Nguyen. So this is a nice talk, actually taking the speed of light as a function of the scale factor A. Because in general, we used to take the speed of light is constant. So that is what gave interest to our group. And that's why we requested you to go for a talk. So the talk is open for discussion now. So the questions are welcome. Yeah, please go ahead. Yeah, Amya, you can unmute and go ahead.
Okay, thank you, Professor, for such an interesting talk. I just had a question about the function capital F of Z that you have. Could you?
Okay, let me go to that again. Okay. Credit space function. What is it again? Yes. Okay. Yes.
Yeah. So I think you have defined it as some C Milky Way divided by C Sn to some power, if I'm not wrong, right?
You mentioned about the formula number 5, right? Is that the one?
Yeah, but I think in the previous slide you have defined it as a ratio.
Yeah, that's right.
Yeah. Right.
Yeah.
So at very high redshift, at let's say infinite redshift, we would assume that we would be at Big Bang. And so shouldn't the speed of light at both those points be same, since there is no A at all? So why make it as a free parameter rather than fix it at 1 is my question.
Okay. Yeah, so this one is okay. We see that the this formula again, everything we talk about this one redshift only appear when the galaxy already forms. So cannot really extend to the Big Bang. Because the galaxy only formed long after the Big Bang, right? I mean, a few hundred million years something. So therefore, this galaxy, we cannot extend this on this redshift to the Big Bang. Okay, because the Big Bang, we need, the structure has to be stabilized already. So therefore, this only apply for that's why I answered in late time only. So this formula again applied for late time cosmology.
Okay, so when you say Z infinity or F of infinity, what does that correspond to?
Infinity means Z very high. I mean that we can see from this formula. But how I should change the notation that let me see here. Okay, so F is function of that, so it means Z very high. Let's say 1,000 or something. Okay. But it still have to extend up to some point. This point will be here the recombination. This one is recombination event. Let's say somewhere here. Okay. And beyond that we cannot do anything. But it's almost Z very large, so it's almost. You see that the change for the F here occur around 2, right? Around here 2, 3, 4 something. But after it almost a constant up to something. So that's why I call it F infinity. But this formula only extend up to the some cut off right there. When the galaxy fall. Before that, beyond that, we cannot say anything.
Right. Okay, I just have one more question. So when you have that table which reports chi-square values, so are those reduced chi-square values or is it?
So the chi-square value, okay, is let me see here a second. Let me open that again. Okay, so where the chi-square? So this is let me show. Did I have the chi-square here? Oh, here it is. So, here it is. So therefore, this is the one. Can you see my screen, right? This is the one. You see?
No.
Okay. See. Okay. Let me see. This one is the. Okay. Oh no. So let me expand this one. Single. Okay. You see my screen, right? So this one. This is the one. Yellow. Okay.
Slide 15.
Yeah. So we compute, you have the DL and you convert it to the modulus, and the modulus model minus the modulus of Pantheon data. Square that and normalize by the error bar from the data from the Pantheon data set. You sum that 1,048 data point, divide by that, normalize it. That would be it. Yeah, that's right. It normalized. So basically that I consider the data point to be independent. I mean, this one is rudimentary in that way. I did not consider the covariance matrix anything to be, this is just to use simple thing, simple thing. Yeah. So that's the formula. Yeah.
So Professor Harku.
Yes.
Yes. Thank you very much, Dr. Nguyen, for this very interesting talk. And I would first of all to mention something that the VSL theories were generated in the 1990s due to a wrong discovery by an Australian astronomer, anyway, called John Webb, who claimed that he observed the variation of the speed of light and of the fine structure constant from the spectra of the quasars. Now, the observations by Webb and some others were proven to be wrong.
Yeah.
So presently, we know pretty sure that the fine coupling constant and the speed of light doesn't vary based on the observations of very far away quasars. So this is an observational fact. Could you please comment on this issue, or did you take into account the quasar observations and this type of issues?
Thank you, Professor Hako. I am happy to answer your question here. So let me go back to that. Number one is that as mentioned here, here. So number one is that if those analysis were reliant on the Lermite formula, then the conclusion from those analysis would be questionable. Because you use the wrong model, then the result can be anything. Okay, that's number one. So therefore, then the time bound in the variation of C cannot be rejected, because if you use the wrong relation. Okay, but number two is that we have to be careful, and the speed of light would vary in the cosmic void. Okay, from this point to this point, they vary. declining. But let us say that the quasar something sit inside galaxy. Right? That is, this is an object which exists together with other star. So therefore, let us say here that the speed of light in the galaxy here and this one here would be about the same. It doesn't really change. As like, this one we have the c to the power, let me show you this. So, where is that again? Okay, this one. This one all is the speed of light in the cosmic void. It varies with that. But the speed of light inside galaxies does not change that much. Okay, and it changed, but by the function of fz and only about 4%. This fz here is changed that, and if you take z here to be infinity, and you show you, in my case, that the fz, the ratio will be changed from the time from the z very large and the z there, it changed about 4%. Okay. So there are two issues with the conclusion from the quasar. That is number one again, it is if they have been using the Mine formula, that is questionable. Okay, alpha doesn't change. I agree with you. The fine structure doesn't change. But because of again this one, let me go back to this case here. Because we know that alpha, how can I draw this one? So edit, maybe I draw something. So how can I draw this one? Okay, draw here. Highlight. Can I use a pen to be new here? How can I use a pen right here? Edit. Okay. Maybe I want to draw some text here. Okay, so here, suppose, here, can I do this? Okay, so alpha is, okay, let's draw here. So alpha is, how can I draw it? Alpha is E squared by H bar C, right? So often we say that alpha doesn't change, so C has to be fixed as well. That's not true. Because don't forget that X bar also changes. Okay, alpha is E squared by X bar C. But because C vary, but S bar also vary such that the product S bar C is a constant. So therefore that alpha doesn't change, I'm happy with that. However, it doesn't mean that C doesn't change because X bar also change. Then it only tells us that X bar multiplied C is a constant. Okay, so that to answer the question. So therefore, from the web conclusion, the how can I draw from here? So we have the
yes.
Okay, let me do this.
Yeah. Thank you very much for your explanations.
Yeah. So therefore, we have. So let me do this.
Thank you.
Yeah, Kappa.
Yeah. So therefore, alpha is squared by X bar, but alpha is fixed. Doesn't mean that X bar and C are fixed because X bar and C can co-vary in such a way X bar and C is a constant.
Thank you, Professor, for your wonderful talk. I'm having one question that you mentioned T naught is insensitive to mu, right? So if we are able to combine that with some other probes, so we can break this degeneracy. So if we are considering some other probes like BAO or galaxy surveys where we are using the standard relation 1 plus the Z is equal to 1 over A, then according to this, that will break down. So if it is so sensitive to the function f of z, then how is it like we should reinterpret that these probes again to compute these results?
Not. I mean, you are mentioned about this graph, right?
Yes. Yes.
Okay. So I'm not sure I entirely understand what you say here, but what I am speculating is that.
Yeah. So
if we can.
Okay.
If we can just say that use CMB because this one is supernovae. So and I say that the supernovae is something about along the time direction. Okay? But the CMB is different. The CMB is one snapshot across the sky at one slide, I mean instant, let's say the recombination time, right? Very thin time slide of time. So the two data sets are kind of orthogonal to each other. So hopefully that when we apply we analyze the CMB using, let's say, the BDS. Let's show you the BDS here. One way that I'm proposing is that perhaps we can repeat this example from BDS, but instead of applying directly for the EDS universe, and we do. perhaps we can redo their analysis using the power law cosmology. So therefore, instead of t equal to raised to the power a t equal to third, we can say that a is equal mu in general. Okay, and in that case, can we also plot in this case we change value of mu, right? Whether we have another curve, I'm speculating. Suppose we have another curve somewhere along this line. Sorry, this is not correct. What I did is I delete that. You see what I mean? I mean, perhaps we have another line along that one, something to constrain that. So that is speculation.
So can we combine it with some other proofs too, other than CMB? Is it possible?
Perhaps, let's say BAO, perhaps like other thing. Let's say, however, the CMB is cleaner than the most because the CMB is fully orthogonal to the supernovae. Because one of them is across the sky, right? The supernovae is along the time direction. The CMB is across the space. So they are orthogonal. You cannot find anything more orthogonal than that. But the BAO or sky survey, whatever it is a mixture. That's the last corrections because it also distributes both in time and space. So therefore it will be less orthogonal. So we have something, we can do that of course, but it's less clean. But of course, everything a data set should be used.
Yeah. Thank
and
you.
By the way, thank you. So by the way, also that I also apply this case for a friend of mine. Also apply this case for the union Cuban one, and we got that result is the same. So
yeah,
we same. Yeah, same. It doesn't depend on. Again, I apply this one Pantheon, but also it also works for the union Cuban one.
Yeah, Sayantan, you can go ahead.
Pardon?
Yeah, okay. Thank you, sir. So for this amazing talk, I just had a question. Mainly, the Hubble tension arises from basically the CMB data. Where do we measure is the spectral indices, right? And spectral indices we explicitly when we take the Newtonian perturbation or something like that, we take the c equals to 1. And in the late time also, we measure the Schultz data or Pantheon data by integrated Sack-Wurz effect, right? I mean, where we also take the c equals to 1. I mean, that's how the galaxies are probably calibrated, like Cepheid, etc. So I'm just asking that when you take c to be variable, I mean, you have already mentioned that for faraway galaxies only you are taking. I'm just asking that where does this degeneracy breaks? Like, I mean, for the spectral indices, if somebody wants to run an n-body simulation or do the Newtonian perturbation or something like that, would somebody has done with the variable c or I mean, how should one do the n-body simulation, or is the z long enough for that? So that's what.
I need to think about what you say here. Perhaps you can email me and we can discuss it offline.
Yeah.
Sure. No problem. Thank you very much, sir.
Yeah. Professor Visham.
Please.
Thank you, Prof. Sahu. Very nice talk, Prof. Nguyen. Just two very quick questions. I may have missed something in your talk earlier on, but can you explain nucleosynthesis? And secondly, what is the range of variation of C? Thank you.
Thank you for your question. Again, this is this work I have not studied that. I have not studied the PAO, I have studied the nucleosynthesis. But again, this one I can tell you that the goal cosmology, perhaps I can go this way. So I mentioned this one. So in 1989, Edward Kohn introduced K matter with the equation of state minus 1/3 within GR. It works within GR without anything new. So this one is the second frequent equation. And with this equation of state equal to this, so this is 0, right? And that means that A double dot is 0, and so A is linear, a linear function of time. And that we call the Ghosting universe. And this model has been rediscovered by Melia and others later on. And they call the linear growth and something like that. I mean, you can go here. So this is one. So this will go and Melia and something, the RCT universe. And recently, now let me go back to that. Okay. Oops, where is that again? No. Oh, here. Okay, good. But so they found some interesting phenomenon for BAO and large scale, and I believe also Media also try to answer your question. for the nuclear, you mentioned nuclear synthesis and so on for that. Now, the problem with this one is that for this universe to occur, to happen, it requires kind of a strange equation of state, right? And that's a very strange matter, form of matter. And also know that this condition is also the zero active gravitational mass. So somehow that the gravitational mass of the fluid would cancel this one out perfectly. Okay, but so therefore this is the key problem for the ghosting cosmology. However, if you go back to the case, let me go back to this case. Okay, but let me go to this. All right, this is the cone case. Let me go right here. But you see that the cone case and the EDS case, what I'm doing here, are all gamma degenerate along the line. Suppose this one is theoretically correct, suppose so. So they are related. That's my point. Okay? And so therefore, even though the cone case here, so the cone case also satisfies the synchronous relation, right? Because in that case, zeta equal to 0 in that case, in the cone case. And mu equal to 1 is for me, mu equal to 1, zeta equal to 0, so also satisfied. So every point along this line is satisfied this condition. Okay, but the cone case has problem because you need to introduce the K matter with equation of extent equal to minus 1/3, which is weird. However, that model may find the justification from this model, from this point. And this point, as soon you it come from this, come from this. Right. If I start from the screen variance action, and it give us this one, naturally. And so therefore that the whole point, this one is that, okay, see here, the cone constant universe satisfy the condition as well because C fixed and A property. But the cone cohomology here is related to our model, our special case, by the change in cosmic time coordinate. And so therefore that, although it has theoretically had a problem, but perhaps that is not too bad because it can be justified by our scale invariance gravity. And that means that the linear phenomenology from BAO structure formation and the question you asked with nuclear synthesis and the early Big Bang may be carried over to the case as well. And that means for future work.
So let us go for the last question, Professor Robert.
Pardon me?
Yeah, we'll go for the last question by Professor Roberto.
No, sorry, I don't understand the question.
No, another one is Professor Roberto is raised his hands. Can you please ask your question?
Yes, I didn't understand it was me. Okay, thank you for the interesting talk. A question about your plots with the fit to the data. In all the plots, the line of yellow dots is inside the black shadow, but it is not in the center. There is a systematic trend from being high on one hand and low on the other hand. Mm-hmm. Can you explain that?
Again, we are dealing with, again, this model had the, how to say this? I would love to have everything to be fully aligned, right? This line. But let's say that if we, this empirical relation. So center around, if we have the prior for mu between 0 and positive mu and positive zeta. So this is a range possible for mu zeta.